Hello, everybody. First of all, I want to thank the organizers for this nice workshop and for the opportunity to present our work here. I have the honor to present work we have done in our group to build an integrated optically pumped magnetometer system that is intended to be used in the Earth magnetic field. Main work was done here in the Institute, but we also had 3 companies working with us. So thanks goes to them as well. The main author of this, let's say, paper and talk is Gregor, my colleague, but he's on a parental leave right now. So it's my honor to present the work today. Short outline of my talk. First of all, I would like to detail a little bit on the working principle we are using for the system I want to present. Then I want to show the system itself, showing the sensor head, the corresponding electronics of the system, and then show measurements we did to characterize and to understand better the system that we have built. So talking about bandwidth, the noise floor, and I will show some shielded and unshielded measurements we did. So the working principle of our system is based on a old, I would say the oldest working principle which is known for optically pumped magnetometers, so-called MZ magnetometer. So what you do is you shine in a circularly polarized light beam into your vapor, and you look for transmitted intensity changes by placing a photodiode. And if you have a magnetic field that is parallel to your light propagation direction, you can see a resonance in the transmitted intensity if an additional oscillating magnetic field, RF field, is in resonance with the Larmor frequency of the atoms. And by this, by the determination of this frequency of the RF field, you can measure your magnetic field B0, which you're interested in. Of course, this is not all we do, but we have another adaptation of this scheme, the so-called light shift dispersed MZ magnetometer, and we do this by shining in slightly detuned, strong, intense laser beam that is off resonant to the ground state of our alkali atoms, where we detect the magnetic resonance. And this detuning of this light leads to a vector light shift in our magnetic resonance. So what you see is a shift in your resonance frequency, which can be explained by or can be seen to be due to an additional virtual static magnetic field that arises due to this light shift effect. Yeah, the light shift effect is also it's not a new effect. It's also known since a long time. And the interesting fact is that this light shift effect changes sign with the helicity of the circularly polarized pumping light. So when you shine in not the sigma plus beam, but the sigma minus beam, this direction of this additional light shift field inverses, and the sensor sees a shift in the opposite direction. And now the idea is, quite natural idea is, to use just 2 vapor cells that should have more or less identical properties. And you use one laser beam with a sigma plus polarization and one with a sigma minus polarization. And this leads you to an absorption spectrum that looks like this. So you see your magnetic resonance lines shifted with respect to each other. And then by taking the different signal electronically or digitally, you can generate a nice dispersive signal that serves as an OPM sensor signal. And the nice thing about this approach is that as you're doing a differential detection, also your inherent common mode noise and technical noise sources can be quite effectively suppressed. How do we do this? So we use a nitrogen buffer gas cell. In this case, when we have a high buffer gas pressure in our cesium cell, the hyperfine lines of our of our D1 transition broaden. And when we use a narrowband laser on this absorption structure, we can just set the relative pumping strength on the 4 transitions by tuning this narrowband laser over our absorption profile. And what we do is we tune the laser to be in resonance with the lower ground state level, F = 3 transitions, because this is also improving our sensitivity. Because when we do a strong pumping on this lower ground state level, we do hyperfine repumping of the state. So all the atoms that would usually populate this lower ground state are transferred to the upper ground state level, where we detect the magnetic resonance. And as we empty this lower state, we can also suppress spin exchange relaxation due to this famous light narrowing effect. And this is also working in a finite field, so in this sense, it's different to the well-known surf effect. So this was just a little bit introduction to this, let's say, the basic principles. Now I want to show the system itself. So it consists of a sensor head, seen here, and a corresponding electronics rack, and the 2 parts are connected by a 10-meter long fiber and electrical cable. So we built the sensor head in, as you see here, with a discrete placement of optical components. We bring in the pumping light by a polarization maintaining fiber, and we heat our cell by another laser that we couple in here by a multimode fiber, and all the optics are glued on a joint glass plate. The vapor cell we use is based on a MEMS fabrication technology we have in-house. In this case here, we have a cell that has 2 measurement compartments that share as a common reservoir where we have our cesium inside. The cell we use here has a thickness of 4 millimeters and a nitrogen pressure of approximately 200 millibars, so it's quite high pressure. A short look into the electronics unit. We have the pumping laser built into this electronic rack. So we use a DBR laser at the cesium D1 transition that we couple into the fiber. We have a second heating laser to have a temperature control of our cell. So typically we operate the cell at around 100 to 100 degrees of Celsius. We have a set of discrete temperature controllers here to control temperature of the lasers and of the cesium vapor cell itself. We have amplifier modules here that amplify our photodiode signals, and these signals are then digitized by on our FPGA board. So the FPGA board is the main part of this electronics rack, and let's say serves for the digitization of the signals. It serves as a digital control interface, so you can configure the whole system by a digital interface. It serves for the generation of the coil current for the B1 coil we are using. It has implemented this feedback loop, digitally implemented feedback loop to track the magnetic field changes. And it has a data interface to stream data to a PC. The whole system is run by on battery, so there's a battery pack included here, which makes the system available for around 16 hours of continuous operation in this configuration here. We did some bandwidth measurements of our system that I want to show. So what we did, we applied just very small oscillating magnetic test fields on top of a 50 microtesla holding field. And you see the blue curve here is the free running mode. And we see that our sensor has a bandwidth of approximately 250 Hertz. If we turn on the digital feedback loop that controls the B1 frequency to, let's say, to control the OPM signal to 0, this dispersive OPM signal to 0, we can see that the bandwidth is unchanged. the feedback loop has one limitation. This is in the frequency resolution of our frequency generator that we use for generation of the B1 frequency. It has turned out that it has a limited resolution that corresponds to approximately 10 picotesla in field units. So to see let's say to consider the sensor signal, we should consider the remaining signal that contains changes that are smaller than these 10 picotesla changes and the corresponding logged signal to get the value information. We did some noise measurements on the system, first in a shielded environment. So we placed the sensor head in our three-layer mu metal shielding room, shielded barrel, and you can see the noise spectrum here. In orange and blue, you can see the two individual channels with the opposite helicity of pumping light, and in green you see the difference. So in green you see the magnetometer signal that we are measuring. So you can see that our white noise is on the order of 100 femtotesla per square root of a hertz, and we can do some more analysis of these noise sources. We compared the measurements to a squid measurement we did in the same environment. By this, we concluded that at the low frequencies, the measurement is limited by the magnetic field noise we have inside our shielding, just because of the noise of the current source we use to drive the field coils. We see a bump here around a few hertz, which results from fiber shaking, fiber vibrations. As you can see, this noise is efficiently suppressed in the differential signal. So this shows that we can suppress common mode noise very efficiently. Around 20 hertz, you see building and magnetic shield vibration noise. So this is typical to all our measurements we see in this magnetically shielded barrel. And what we also see, if we disconnect or if we make our sensor magnetically insensitive, for example, by just detuning the RF field, we see that our electronics noise limits us to approximately 100 femtotesla per square root of a hertz. But on the other hand, we found if we disconnect the cable, so the cable running from the sensor head to our electronics, the electronics noise drops down by almost an order of magnitude. So we concluded that that's why we have an electrical pickup noise into our cable. So and in this sense, we have a straightforward way now to improve even further our sensitivity. So because the intrinsic fundamental sensitivity we have calculated for our system is on the order of 12 femtotesla, coming from the atomic spin projection noise. So this would be the absolute ultimate limit that we could achieve with the system. We did some unshielded measurements, also in comparison with the squid system that we have in-house. And you can see the time trace on the right side here. So the low frequency trend is really identical. The corresponding noise spectra also look very similar. At low frequencies, the OPM seems to be a little bit superior to the squid measurements, and we believe this is due to the working principles of the OPM. OPM is a scalar sensor, and it's not so susceptible to vibrations. The squid is a vector sensor, and it measures the three components of the field independently, and the balancing of these three magnetometers is just a little bit more difficult than for an OPM as a scalar sensor. To relate to some commercial OPM systems, we collected data from all the vendors we know that deliver systems to be used in the Earth magnetic field. Yesterday, we heard a very nice talk about the new system that is built by TwinLeaf now. They claim even to be at 200 femtotesla per square root of a hertz noise floor. So they are coming quite close to our demonstrated noise there. Of course, we have to be fair and say the footprint of our system is, of course, a little bit larger. But in terms of sensitivity, we have still a little advantage at least. So to conclude my talk, I have shown a portable OPM sensor system that we have developed here in-house, showing a 100 femtotesla noise floor and 250 Hertz bandwidth that is operating at Earth magnetic field strength. We have identified limitations of the system in the noise level, and we have straightforward routes to further improvement now. And this is the work we are doing at the moment. So we're working towards an advanced version where we also want, of course, to miniaturize the sensor head further and also to strongly reduce the electronics footprint of the system, that it gets more handy. And and for this work, we're also looking for motivated students. So I can advertise a little bit here, I think. And with this, I would like to thank you for your attention, and I'm happy to answer your questions now.
Awesome. Thanks, Theo, for a nice talk. I'm applauding. Other people probably applauding too. You just can't hear it. And I would say that we have 5 minutes for questions, or maybe 4 minutes.
Okay.
Just to like catch up a bit. There was already one question in the chat by John Bainbridge, and that is, what is the total power draw of your system? What's the capacity of your battery pack?
Yeah, as I told, in the current setup, we can work for approximately 18 hours. So, and I think the total power consumption is on the order of 15 watts. So most of the energy is used for the heating of the cell, because we have to heat our cell to approximately 100 degrees. And I think this alone needs on the order of 8 to 10 watts.
Cool, thanks. Are there more questions? I might have one, and that is, how does your system react to gradients? I mean, you make a spatially separated measurement to generate a dispersive magnetic field signal, but how does it react to gradients?
So I think we can consider two different things. So let's say gradient between the two cells. Yeah. So this would just be averaged, because let's say cell with the sigma plus light sees a little bit smaller field than the cell with the sigma minus light. So then you would naturally average this gradient. You still measure the average of the magnitude of the field, and gradient over the cell volume would of course broaden your magnetic resonance line in case the gradient is makes a broadening that is larger than your magnetic resonance line. In our case, we have line width of approximately 1 kilohertz, which would mean you could tolerate gradients up to 350 nanotesla over your cell. So I think this is quite relaxed in this sense.
There's another, there are more questions coming in. I mean, you can read them yourself, or I can read them.
Yes, I can read it. It's by Kasper Jensen.
No, there's one before by John Bainbridge again about, do you keep everything DC? Yes,
we do. there's a custom-made, so the electronics is mainly made by our spin-off company, Supracon AG. They have a long tradition in building such systems, and they keep it DC. Yeah, it's all specially designed for DC operation. So I hope this answers the questions, and I would just continue with the question Kasper Jensen wrote. You use a vapor cell with a reservoir and 2 small chambers, which are all connected. Would there be any difference if you just used one big chamber? No, in principle there would be no difference, as long as you can separate the 2 atomic ensembles. So in our case, we have quite a high buffer gas pressure, which leads the atoms to be spatially confined. So in principle, you could also use just a big vapor cell, of course, that you have where you have the beams separated with each other.
Cool. I think that is that should be it for this question round. So thanks, Theo, again.
Thank you very much.